Okay, so back where we were last time, we were talking about this idea called flux, and keep in mind the idea of flux over a curve in 2 dimensions is a total ripoff of the idea of flux through a surface in 3 dimensions. In both cases, we have fluid moving, and we want to know how quantity in some appropriate sense, quantity of fluid per unit time passing over or through a curve or a surface. Okay, so we did some work last time to figure out how to do this through a boundary, specifically a boundary. And the first thing we did is just write down what happens when you add that up over an entire boundary curve. Then we did some fancy geometry, talking about how that dot product is equal to that dot product. That allowed us to translate that. Oops, I missed the thing. Translate that a little bit, and that allowed us to rewrite it in terms of regular old vector line integrals that we have tools to work with, right? So we've not really previously seen this integral of something dot in ds, unfamiliar construction, not sure what to do with it, but dot dx, that's, we've got experience and tools that allows us to deal with that. So, for example, Green's theorem. Now, this is where the heavy lifting happens. Green's theorem is where we're, pulling out the big gun to actually change, very huge step here where we change a line integral into a double integral over the interior. And then, some details follow. Okay, fine. So this is about where we left off. What I want to start with today is the observation that we can take a completely different point of view on how to relate boundary flux to a double integral over the interior. And that is to completely disconnect from Green's theorem entirely. Again, here's where we used Green's theorem right here. And again, Green's theorem did our heavy lifting. Had we not known Green's theorem, we wouldn't have been able to do any of this. Right? So if we were to say, let's kind of set aside Green's theorem, could we come up with this result on our own, independently? And the answer is yeah, sure, absolutely, because of this key point right here, boundary flux by itself. Forget about vector line integrals. Boundary flux is its own accumulating quantity. Boundary flux, just like circulation, boundary flux has this feature that the whole is the sum of the parts. So in particular, if you look at the outward-oriented boundary flux for the left piece of area, and if you look at the outward-oriented boundary flux for this right piece of area, you're going to notice again, kind of analogous to what we saw with the circulation business, but there is this shared edge where I sliced it, right? And yes, that's going to be part of the boundary of D1 integral, but oriented that way. But it's also going to be part of the boundary of D2 integral, but oriented the other way. And again, same edge, twice, with opposite orientations, and they cancel. Right, so now this was the most of the sort of the big picture idea of how we came up with Green's theorem. It's just that with Green's theorem, the opposite orientations were 2 different directions. I guess it'd be like this: 2 different directions along this shared curve. Whereas here, we're talking about 2 different directions through this shared curve. So geometrically different, but strategically pretty similar. So the punchline is you can just write down your own accumulation theorem for boundary flux. And the details are some things to be written down and some computations to come up with what that integrand should be, blah, 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 etc. A bunch of details. The punchline is the exact same theorem that we already had. So we're starting to collect what I'm going to call accumulation theorems. And here's the 3 we've got written down so far. We're going to pick up another couple of them today. But the very first one, this goes back a couple of months, I suppose. mass is an accumulating quantity, and so we can compute it as an integral of density. And this was basically, this is our motivation to write down double integrals in the first place, almost. I mean, it goes almost that far back. Nothing particularly deep or scary about this statement. Mass, yeah, the sum of the parts, that's how mass works, of course, right? And then mass relates to area by way of mass per unit area, right? This idea of density. All old news, old ideas. Significantly less immediately satisfying, but totally analogous, is this next theorem, Green's theorem, that we saw a few lectures back. And I argued that even though it's not physical, even though it's not actually, concrete, actual stuff, circulation, a little surprisingly, but nevertheless, circulation is an accumulating quantity. So its whole is the sum of its parts too. And likewise, there is this notion of density. Stuff relates to size by way of stuff per unit size, aka a density. Then again, to be fair, the stuff is a weird kind of stuff. The stuff is circulation. It's not physical stuff, but it behaves like stuff, so you can treat it like stuff. And in that sense, this is really just stuff per unit size, the stuff being circulation. And that's the term circulation density. And then, analogously, what we did sort of just now is to take all of this and just kind of take all these same ideas and apply it to, instead of circulation, applying it to now boundary flux. Because again, boundary flux, accumulating quantity, as we saw up here. Anytime you have an accumulating quantity, you can write down what you might call a density integral. Which again is all I'm doing here. I argue the whole of the sum of the parts. Again, accumulating quantity, so okay. And then stuff is stuff per unit size times size. So structurally, these three results are all, kind of the same thing, right? Very highly analogous. It kind of leaps off the page the way I've got it written down here. That was on purpose. What I think makes this really useful is that while these are new and weird and, hard to kind of get accustomed to, this is not, right? This is old and familiar, right? So what I want to encourage y'all to do is to take the ideas that you are hopefully and presumably comfortable with up here with this first theorem and help that get you accustomed to the idea of thinking analogously about these last two new theorems. All right. So, 3 accumulation theorems. Here's a fourth one. Fundamental theorem of calculus. I know y'all already know the fundamental theorem of calculus. You've seen various different versions of how to think about it and what to do with it and stuff like that, and that's all well and good. I'm going to give you a deliberate, specific point of view on it here so that you can see how it, too, fits in with our developing collection of these accumulation theorems. So we normally think of the fundamental theorem of calculus as you have an integral and you compute it with a formula. I'm going to think of this kind of backwards from that. I'm going to think of it as we have this quantity called change that I'm going to denote by capital delta. And I want to figure out how I can view change as an accumulation. So first, I argue change is an accumulating quantity. Now, that's a weird way to think about it. I think you got to give it to me. That's true. So, for example, if I look at how much my height changed between the ages of 0 and 5, and how much my height changed between age 5 to 10. Well, if you add those up, you're going to get the amount that my height changed between ages 0 and 10, right? I mean, the change the sum of the individual changes is the total change. You can say it in various different ways, but it literally is an accumulating quantity. So once you make that realization, change is an accumulating quantity, you write this down, and then you can also talk about the corresponding density, stuff being stuff per unit size times size. And along those lines, this is an interpretation of the derivative. Weird, to be fair. A weird interpretation of the derivative. And I know you have probably preferred interpretations of the derivative, right? But the interpretation we're going to take here is that the derivative is a density. Don't think of it as the rise over the run. Think of it as change, this accumulating quantity called change, per unit size, dx being size. So as in this picture here, you can talk about this is the amount that the function changed over this little subinterval. And again, you could think of this as the rise over the run, and this is a slope. Or you can remind yourself that the change is an accumulating quantity. This change is a kind of a stuff, and in particular, this amount of change happened on a subinterval of this size, and so stuff per unit size density. Okay. So, weird point of view, I know. But it's going to be super useful for us as follows. Again, I'm a big believer in analogies. And when you find a strong analogy, we're going to have a bunch of them in this last few weeks of the class. When you find an analogy, then you can use what you understand about one of them to help you kind of wrap your brain around the other one. So, looking at the fundamental theorem of calculus again, and here's the, let's see, let me zoom out just a bit here. Try to get this just right. Okay, close enough. Here we have a function. You can see we're looking at how this function called f changes. I'm looking at the graph. Graphs are great pictures for single variable functions. I can see that this over this interval from a to b, there's clearly a certain amount of change, right? The function changes a certain amount. So, reminder, when you have an accumulating quantity, I pushed this idea last time that you might measure it on the boundary, but it actually happens in the interior. Now, I'm going to scroll way back to where we were, I guess, last time. Yeah, so this picture here. And this was a tough idea to choke down. Sort of seems counterintuitive. This idea that even though you measure circulation on the boundary, I'm going to encourage you to think of it as happening in the interior. And that's not only somehow allowable, but that's actually useful and to be encouraged. So a little bit of a weird idea, pretty uncomfortable, but now let me notice what we have here. Let's see here. Now, another accumulation theorem. And look at what we're measuring. We're measuring change. Whoops. Sorry, I want to be in the highlighter mode here. Measuring change, how much the function changed. That comes from looking at the value of the function at A and the value of the function at B. So change is measured on the boundary of our interval. But I'm going to argue again, and hopefully much more believably this time, even though it's measured on the boundary, it's happening in the interior. Now, again, easy pitch. If I were to try to persuade you that this change from this value to that value, if I were to try to persuade you that it happens in the interior, well, of course it does. Look, there you can see it happening, right there on the graph. So that's where the function changed, specifically at these points in the domain. Right? So what we have here is, I like to think anyway, and I hope you would see it the same way I do on this, a very satisfying, dare I say, obvious example of something that's computed on the boundary actually happening in the interior. An accumulating quantity, no less, measured on the boundary that actually, literally happens in the interior. Right? So keep this in mind, right, as you're trying to persuade yourself of, again, this story that we were discussing last time or time before, whenever that was, of the analogous assertion that I'm making here of something computed on the boundary, circulation, and this hard-to-swallow idea that it is actually happening in the interior. Okay. All right. There's even more that we can get out of this. Not only does this story, I think, make it pretty easy to believe this business about the interior, but in fact, the derivative, or let me say it differently, the density, the integrand in your new integral that you create, tells you, in fact, literally where and how much in the interior that thing is happening. So let me try to draw a picture of the derivative here. The derivative would look kind of like this, and then somewhere along in here it starts to go up, and then it kind of levels off for a little while, and then somewhere, I didn't do that well. Let me try again. It goes along like this, and then it increases up to some level, and then it stays level, and then it comes down about like that. There's the derivative. I don't remember your curve plotting stuff from Calc 1 long ago, I hope. And so I claim this is the derivative telling us where this interior specifically is happening in the domain. It's not happening here. The derivative is 0. There's no change happening here. None there. Some here. More there. Less here, and then back to none there. So the derivative is explicitly telling us, again, not only that changes are happening in the interior, but where and how much by the value of that density. Is that cool? And again, that's easy Calc 1. Weird language applied to easy Calc 1 ideas that I know y'all are already comfortable with. So I'm gonna do a pointlessly, seemingly unnecessarily explicit example here of what I mean by the derivative tells you where and how much the change is happening. By looking at this example here, and I've got this function, you can see a plot of that function. There it is. It's perfectly obvious how the change is happening. And again, y'all have fantastic intuition for this function. And you know how to take the derivative, blah, blah, blah. So here's an odd question we could ask. Where is this change happening more? Is it happening more at x equals 1 or x equals 2? Looking at these two candidate points, which one of these is the function changing more? Or said differently, of all the total change that happens to this function, where, between these two candidates, where is most of it or more of it happening? And the obvious answer is to say, well, I mean, for crying out loud, look at the picture, my God, it screams perfectly obvious that this one over here, right, where x equals 2, geometric intuition. Short that geometric intuition, you could look at the derivative, and the derivative gives you, slope, and you could think in those terms. But let's think in terms of densities. If you want to know where something is a lot, you want to know where the density is highest. The derivative is the density, and you could just straight up compute that density at our two candidate points, right? Plug in x equals 1, plug in x equals 2. And you can just see where it's bigger. And frankly, it's bigger at x equals 2. No picture required, no geometric intuition required, no previous understanding of slopes required, right? Density tells you where stuff is happening and how much. Simple as that. Okay, so again, silly example. Why are we doing that silly example? Well, because I claim something totally analogous applies when you're talking about circulation. So this one, let's walk through. Now, this is a much more complicated scenario. We have a vector field, for crying out loud. The domain is two-dimensional. The field vectors, also therefore two-dimensional. I'm not looking at a graph. I can't sort of cheat by over here on the side where no one's seeing what I'm doing, draw the graph and try to gain intuition off of that. I can't. It'd be four-dimensional. So we really don't have any cheat sheet on this that we can work with. So nevertheless, though, let's ask, where is the circulation happening and how much? All right. Well, if you look at circulation, here's the boundary, orientation and all. Let's ask, how much circulation do we have in the first place? And I'm going to make the observation that there's some negative circulation happening up here on sort of the top because, look at this piece right here, right? So the flow is that way, but the curve is going that way. It's going the opposite direction. So to what extent is the fluid flowing in the direction the curve is going? It's quite the opposite. Right? So we're picking up some negative terms along this top edge, but down here we're picking up some positive terms because down here on the bottom piece you can see we're going literally exactly the same direction that the curve is going. So negative terms from up here, positive terms from down here, but these are small negative terms because look how small the vector field is. These are large positive terms down here because look how big the vector field is. So small negative, big positive, that adds up to positive. So grand total, there is a positive amount of circulation, and you can see that right there on the boundary where we, I confess, where we measure circulation. But now let's ask the related question, where to come from? Right? In the same sense that from this picture, I see change. I measure the change by looking at the boundary. Yeah, but where did the change actually happen? Where did the change come from? And I claim that the density, namely the derivative in this case, is the algebraic tip-off of where that change is happening. So along those same lines, I claim Green's operator will be the tip-off here. And if you were to have an explicit formula for this vector field, you could compute Green's operator explicitly, and it would just tell you how much of the circulation we just sort of, I'm going to say measured on the boundary, how much of that's happening where. Now, we don't have a formula on this. This is just kind of a hand-waving example, but let me try to argue with intuition. Suppose I look at that green little region here. Imagine that being a leaf. Imagine our vector field representing a flow of a fluid, right? Like this is a little creek or river or something like that. Drop a little leaf onto there. The leaf floats downstream. Is this leaf going to be turning? I would observe that it's being pushed on this side and this side by kind of the same amount. This is like, you're pushing a shopping cart by holding on to both ends. The left side of the handle, the right side of the handle, you're pushing it symmetrically. It's just going to go straight. This leaf here is just going to float downstream without any twisting at all. And if you were to compute Green's operator on this, if you had an explicit formula for the vector field, you'd get 0. And that is Green's operator telling you specifically that of all this circulation you measure on the boundary, none of it's happening there. And likewise, same story down here. Now, if you were to look at you drop a leaf right there, now it's being pushed harder on the what you might call the top side, which you would think would push it sort of clockwise, make it want to spin clockwise. And it's also being pushed harder on the bottom side that you would expect to be turning it counterclockwise. Grand total then is being pushed the same amount on both sides. This too, you would expect would just roll downstream without any turning at all. So Green's operator, if you were to compute Green's operator for this one, likewise, you would get 0. But if you were to drop a leaf right here, that blue leaf, what would happen to that leaf? Well, it's being pushed a little bit on the top side, thus there's a little bit of a force kind of making, you would suspect, making it want to turn clockwise. But there's more pushing on the bottom side, which you would expect to turn it counterclockwise. We should expect, looking at this blue leaf here, you would expect not only would it go downstream, but it would be kind of turning. It'd be rotating as it rolls downstream. Counterclockwise would be my guess. And so does Green's theorem track on this? And yeah, absolutely. On this one, if you were to have a formula for your vector field, and if you were to compute Green's operator in this region here, you would get a positive answer, because those leaves are spinning counterclockwise in that region. So altogether then, again, remember our goal here was to ask where is this circulation that I've measured on the boundary? Where is that really coming from? What's causing this total circulation that I measure on the boundary? Well, it's this gray area right here, right? That's where you can see there's a sort of an inconsistency in how we're pushing things. This gray area in here is where the leaves are kind of turning as they float downstream. Forget about this white zone. There's no circulation coming from up there. There's no circulation coming from down here. Just like the derivative tells us, yeah, there's no change happening over here, and there's no change happening over here. The change is all happening right here. Okay. Okay, now totally analogously for divergence and flux, I'm going to be quicker with this one because it's morally equivalent to what we just talked about. So let's look at the outward-oriented boundary flux. Here's our boundary. Keep in mind when you're talking about flux, the convention orientations are outward, because we're talking about how stuff flows through, not along. Yeah, I claim you're going to get some negative flux terms over on this side because the flow is inward, not outward. You're going to get some positive terms over here because the flow is outward, as it should be. Right? So positive there, negative here. Yeah, but there's a small vector field over here, so it's a small negative. Longer field vectors over here means we have a large positive, and large positive, small negative, again, that adds up to positive. So we would expect a positive amount of boundary flux, again, if I had formulas to work with here. Positive amount of boundary flux there. So again, where is that coming from? Where is that flux happening? I claim it's going to be that gray region. Again, specifically, if you look at, some little region about like that, this green region here, well, there's flow inward. There's also flow outward. The vector field constant along in here, so that means it's exactly the same amount in as it is out. Flux 0. And if you had formulas to work with, you would find that algebraically, that in fact, the divergence. Wrong color. The divergence here would be 0, and likewise, not only there but also over here. So that's not where this flux is coming from. Again, we have measured empirical flux on this boundary. It's not coming from the left white region or the right white region. The flux would be coming from in here. You can see there's a little bit of inward flux on this blue region, but there's more positive outward-oriented flux on the right, adding up to a net positive amount of flux happening here. And divergence will indicate that. When you compute the divergence here, you're going to get that this divergence would be positive. So again, the divergence, let me say this in more general terms. The density, appropriate to the quantity we're talking about, of course, the density is positive here. That's where it's happening. The density is 0 over here. This quantity called flux, so yeah, none of that's coming from over here. Okay. All right, so we can make this algebraic too. This example here is a non-trivial, definitely worth saying, definitely hard to figure how you would answer this question any other way, analog of this silly example right here that we kind of laughed at as we were going through it because, oh my gosh, it's so clear, of course. Obviously, there's more change happening where it's steeper, right? I mean, of course it is. Steeper, therefore more change. But specifically, we took the point of view that the derivative, don't think about it in terms of steepness, think about it as a density. And where the density is greater, that's where more of the quantity change is coming from. So, same deal with this example. Weirder example. I have some wacky vector field. I don't know how to draw a picture of this. I can't look at a picture of this and just immediately intuit from geometric experience or other points of view or anything like that where the flux is coming from that I would measure on the boundary, where the circulation is coming from that I would measure on the boundary. I don't know. Hard to say. But we can do the algebra. And to the extent that you're interested in circulation, let's again with the mode here. To the extent that we're interested in circulation, where is the circulation coming from? Yeah, look at the circulation density. Circulation density is Green's operator. Look for where the circulation density is greatest. And of my two options, the circulation density is greatest at this point. So you see here. So that, between these two candidates, is where more of the circulation is coming from. More of the quantity is coming from where the quantity's density is highest. Likewise, to the extent that you're interested in flux, right? Well, we're going to look at the flux density, aka divergence. You look at your flux density, see where it's the biggest. And the flux density is biggest at that point, as you see there from the arithmetic. And so that point is where more, as opposed to the other point, where more of the flux is coming from. Again, the density gives it away. How we doing? Okay, so again, reminder, we came into this conversation looking at these three equations right here. I'm calling them theorems, if you will. Three different statements, anyway, about accumulations, right? And I make this pitch that analogies are useful. Analogies are powerful because when you have some really strong analogy like this, what you understand about one will give you strong hints about how to think about the others. Right? And so now we've added to this list a fourth accumulation theorem, fundamental theorem of calculus. Fundamental theorem of calculus, again, we have strong intuition for the derivative. The derivative clearly tells us where quantity change is happening. And so by analogy, as we've just gone through in detail, these densities. Likewise, tell you where these quantities are happening. Where this integrand is highest, yeah, that's where most of the mass is. And likewise, where Green's operator is higher, that's where more circulation's coming from. Where divergence is higher, that's where more flux is coming from. Pretty literally, at least in terms of intuition. Okay, moving along. Accumulation theorem number 5. New theorem right here at the start of 6.3. By the way, the book doesn't do the topics in 6.3 in the same order that I do. I think they take anyway. There's always different points of view, and that's fine, whatever. I like to start with this. It's called the fundamental theorem of line integrals. You can see the punchline right there. You can see probably why we call it fundamental theorem of, and that's because structurally it looks just like the fundamental theorem of calculus. So we're ripping off the first half of the name because, oh my God, it looks exactly like that old familiar theorem. The difference, of course, being that this is a theorem about vector line integrals. Thus the second part of that name. That all seem kind of believable? Okay. All right, so let's see, how are we going to understand this theorem? Again, there's different ways to go on this. Lots of valid and reasonable and useful points of view. What I'm pushing here, obviously, very much is this idea of accumulation and density, right? And so that's the take that I want to present on how to think about this theorem, is that this is about an accumulation. And the accumulating quantity is change, again. Just like with the fundamental theorem of calculus, change is the quantity that I want to think of as sort of adding up. Now, how is that the case? How is it that change accumulates over this curve? And this is just a hand-waving kind of, intuitive point of view I'm going to give you. Imagine this is a mountain road. Imagine I'm interested in my altitude as I drive along this road. Well, there's a certain altitude here. There's a certain altitude there. There's another altitude there. And if I know how much my altitude increases between these 2 points, and if I know how much my altitude increases between these 2 points, if I add those up, I get the altitude increase, the altitude change over the whole. So, again, quite literally, the whole is the sum of the parts. And so change, defined like so, again, is an accumulating quantity. It accumulates over curves. How are we doing on that? Everybody happy with that? You can write down the algebra if you like. Y'all probably seen things kind of like this algebra before, and in particular this f of x1 and this minus f of x1, they kind of cancel in the middle. Right? If you like that one of you. Okay, so we have an accumulating quantity. That means we can talk about the associated density. How does change relate to distance? And this is just a bunch of chapter 2 right here. If you want to know how much does the function change, in other words, what's my output change for my function, and you want to know how that relates to my input change, dx, for the function, well, this is an old chapter 2 formula. Input change and output change are related by dot product with the gradient. This is a real valued function f, so there's no matrix to talk about. I guess you could say it's a single row matrix, but that's not really needed. Dot product with the gradient is sufficient here. And then I rewrite that ever so slightly. You'll recall, of course, that we have a bunch of different formulas for dx. Here I want to rewrite dx as tds. You'll see why momentarily. Of course, there's different ways I could have written it. Altogether, I have that output change let's see, let me do it like this. Output change relates to size by way of this equation, or saying that a little differently. This accumulating quantity distributed over something of this size, the relationship between them is change per unit size. Accumulating quantity per unit size, namely density. So this thing here that I multiply by the input size to get output quantity. That's my density. So, we have all the pieces ready to put together again. Analogous to other theorems we've seen. The whole is the sum of the parts, accumulating quantity. By the way, I'm going to come back and talk about this stuff later. So for the moment, let's just ignore that. But so for the moment, the whole is the sum of the parts, and this equation here tells me that stuff is stuff per unit size, namely a density times size. What do you think? Everybody all right? Bam, theorem, right? Brand new theorem. In fact, specifically the theorem that we've stated above. Vector line integral. Okay, to be fair, one of my less preferred notations for a vector line integral. But nevertheless, vector line integral computes stuff. F of b minus f of a. Okay, now let's change our notation. Let's remind ourselves that TDS that I have right here, right? This TDS is dx, right? So this is really kind of a better way to write the vector line integral. It's certainly a more compact way to write the vector line integral. So how would I make sense out of this connection here? How do I see a density in this? Can I just call the gradient a density? Not really. If you think about it, every density we've ever seen before, density is a scalar quantity. We don't have any idea of a vector density previously, right? And furthermore, every density we've ever seen is stuff per unit size. And so specifically, this would need to be a scalar notion of size. So this is just not really set up very well for our existing idea of density. But remember, we've already kind of done a bunch of reinterpreting, being flexible on the idea of a density, right? It's not always about mass. It can be about any kind of a stuff. It doesn't have to be per unit volume. It can be any kind of a size. Doesn't even have to be physical stuff. It could be algebraic stuff like we've been talking about. So here's the next flexibility, sort of interpretational leeway that I'm going to ask of y'all. And that is, let's try to interpret this, even though it's not exactly size, let's think of it as oriented size. After all, dx is two things. It's a vector, right? So vectors are two things. They're a magnitude, which is literally the size. A magnitude and a direction. And the direction we can think of as an orientation. It's telling you how the piece of size ds, which direction is that pointing? Right, so I think this is a pretty natural take. Again, thinking flexibly and loosely. We can think of this dx as being an oriented size. And if you do that, then we can interpret the gradient as an oriented density. Stuff relates to oriented size by way of an oriented density. It's just a kind of an interpretation. This is just a way of trying to make sense out of this blue equation. in terms of the vectors that we sort of see in having written it this way. It's very handy, though. Okay, so the hard thing to get used to is what I have here in green. This is a weird idea that a density could be an oriented thing, that a density could be a vector. So again, it's just a point of view. By the way, I have a goal in mind for this. This is laying a little bit of groundwork, trying to plant ideas in your head of sort of getting used to this weird idea of an oriented density. Because when we get to 7.3, we're going to have a pretty nasty problem on our hands, which is to try to figure out what on earth is this thing called curl. And the visualization challenges involved in that are very demanding. It's geometrically very hard. And ultimately, what I think makes the most sense, what gives the most help in having a geometric, intuitively satisfying, intuition, I think I said that word twice, for curl, this thing called curl, is to be comfortable with the idea of an oriented density. Ultimately, curl also is going to be an oriented density. All right, so this is just laying a little groundwork, planting a thought. Let's do one. Looking back up at our theorem here, you can see we took a weird point of view. We started with change, and then we developed that you could think of change as an integral. In practice, when we use this theorem, we go the other way. In practice, when we use this theorem, most of the time you start with an integral and you compute it with that formula. So that's what my example is going to be. Notice what we need to make that happen. I need for my vector field to be a gradient of something. Right? It says so right here. If you're going to apply this theorem, you need your vector field to be a gradient of something. So my F has to be a gradient. And then notice further, I'm going to need to know what that thing is, because that thing whose gradient is my vector field, that's the thing that I'll be plugging into, to use our handy-dandy formula. So, by the way, the book notes, this is a standard term, very heavily used in physics, and I imagine probably also engineering, and I know most of y'all are engineers. The term here for a vector field that is a gradient of something, the term is conservative. There's a really good reason for this term, conservative, and it has to do with potential energy and kinetic energy and conservation of the total between the two, and under what circumstances it's possible. I like to point out at a time like this that we already have a word for a vector field that is a gradient. The word is gradient. Right? Boom, right there. We didn't have to go anywhere, make any efforts for that. So you're going to hear engineers and physicists use this term conservative. You're going to hear me just say gradient because it's easier. Sorry, you had a question.
Oh, yeah, you just answered it.
Oh, okay. Yeah, good. Okay, so all that said, here is an integral to be computed. Right there, vector line integral, vector field given, curve given, curve pre-parametrized for us. Isn't that nice? So it might seem. That's actually a red herring. That's a distraction. Make sure to remember you have a bunch of tools in your toolbox for how to compute vector line integrals. We can parameterize and pull back. Sometimes we can use Green's theorem if certain conditions are satisfied. Sometimes we can use the fundamental theorem of line integrals that we just learned, again, if certain conditions are satisfied. You have various options. Don't let the statement of the question bias you arbitrarily in one direction of your, which tool should you choose, because maybe the other tools might be better. And in fact, that's exactly what happens here. Now, you could totally parameterize. I mean, here's your parameterization. This is your formula for x. So cosine t goes there and there. And sine t, that's your y. That goes there and there. And you plug in, and don't forget to take your x prime. That's going to have sines and cosines. What you're going to have here is some trig integrals that involve like half angle formulas and all that annoying stuff like that. So you can do these integrals, but if you brute force this, it's going to be tedious. So let's consider the other option, and that is to use our fundamental theorem of line integrals. Let's ask, is our vector field here, is that a gradient of something? And why, yes it is. Isn't that nice? Check it out. This function right here, x squared, y squared, its gradient is exactly our integrand. So we, in fact, this is not just an arbitrary, random vector line integral off the street. This is a special vector line integral of a gradient, aka a conservative vector field. And so we can use the fundamental theorem of line integrals. Again, it's just a matter of plugging into this function. You just plug in the endpoints. The endpoints are easily computed. F of b minus f of a. Bam, done. No integrating required. Awesome theorem. Y'all have a great day. See y'all on Wednesday.